Hello students, let's begin lesson 6, Discrete Probability Distributions. In section 0 of this notebook, you can find a brief review on probabilities, which we covered in lessons 4 and 5. The detail is left to the students. Now let's go to section 1, Random Variable. A random variable is a scheme that assigns a numerical value, which we call the payoff, to each outcome of a sample space. More precisely speaking, you can call it as quantitative variable or as a real valued function, but that's a bit too deep, so you can consider it as any kind of scheme. If you just put numbers into outcomes, there goes one random variable. Here's an example. Let's consider an urn model, as we did before. An urn contains 5 red balls, 3 green balls, and 2 blue balls. Now, with just colored balls, we cannot do a lot of mathematics. I mean, RGB, which gives rise to this sample space, RGB, but those are just characters, not numbers. So the kind of mathematics you can do is rather limited. Yes, of course, you can count. There are 5 red balls, 3 green balls, 2 blue balls out of total 10. So you can do some probability computation, but that's about it. No more of that. Now let's consider some random variables. That is, let's assign numbers to each outcome of the sample space, like this, for instance. If you get a red ball, then you get nothing, $0. Draw a ball, and if it is green, then you win $2. And if it is a blue ball, then you win $3. So payoff gives you a random variable. There goes one example of a random variable. Here's another. Same game, same rule, but consider that you have to pay $1.50 each time you play the game. So for red, you get nothing, but you have to pay $1.50 to play the game. So the net is minus 1.5. If you get a green ball, then you won 50 cents. If you end up with a blue ball, then you won $1.50, 1.5. Of course, you can play something completely different with something completely different rule like this. In this case, the distinction between red and green does not exist because as far as this random variable, this payoff structure is concerned, red or green, they're both negative 1.25, the same as before. I mean, they're the same, so they're indistinguishable. So in this case, you can consider only 2 outcomes. Negative 1.25 versus 4.75. In this case, or that case, you can consider 3 different outcomes. Now, along with all these numbers, we can do a lot more mathematics. And that's what random variable is all about. What kind of mathematics? Well, here's an example. Let's consider this. Find the probability that this x is the first game, this x is less than or equal to 2. All right, less than or equal to 2. So what do we have? 0 or equal to 2, but no blue. Does it make sense? So in short, x is less than or equal to 2, which is written in terms of mathematical expression, corresponds to red or green. Consequently, you can add up these probabilities. For red, 0.5. For green, there are 3 green balls out of total 10, so 0.3, so you end up with 0.8. Here's another example. For the second game, the probability for y giving you strictly greater than 0 and less than or equal to 1.5. Let's see, strictly greater than 0, negative 1.5, so that's out. 0.5, okay, that's okay. 1.5, how about that? Is it yes or no? It's less than or equal to, so yes, it qualifies. So green or blue, so green plus blue, so you end up with the probability of 0.5. Does it make sense? What if you change a problem like this, for instance? If this is strictly less than 2, then let's see, in this game, strictly less than 2, so red is okay, 0 is strictly less than 2. Green is not okay because equal to 2, but now I change the problem to strictly less than 2, so I just get red only. So the answer is 0.5, and that's the end of the problem. So in short, the mathematical formulation corresponds to some further argument like R or G or G or B, those logical expressions on events. How about the next example here? Probability that Z is equal to negative 1.25. So it's going to be red or green. So red or green, add it up, you're going to get 0.8. You can do a lot of other probability computations like this, associated to some algebraic expressions of x, y, or z. And that's one example of a random variable. And we can do all these because we assign the numbers. With RGB, we cannot make any kind of mathematical expression out of these. Okay? So that is one of the big purposes of the random variable. You can do a little bit more mathematics. Actually, not just a little bit, whole lot more mathematics, because we now have more numbers. Now, all these examples are discrete random variables because we have only a discrete set of values. 3 possible values or 2 possible values, they're all discrete. And here are some examples of discrete random variables. Let x be the number of dots when one fair die is cast, 1 through 6. So it's a discrete random variable. Toss a fair coin and assign pi for head, e for tail. We have discrete random variable. You see, I've seen some students who get a little bit confused. Discrete means integers only, but integer numbers, we have 2 possible outcomes, and that's integer. But pi or e, neither is integer, but it's still okay. They can be real valued. All the random variables discussed in previous example, they're all discrete. As a matter of fact, I labeled it wrong. Sorry about that. I should have said 1.2. And the final example here, a random variable q that takes all non-negative integer value given like this. And this is also a discrete random variable. It is known as Poisson random variable. And, as you can see, it is associated to a certain name. So it's got to be something important. But I don't think we'll discuss Poisson random variable at this level. If you go over to a little bit higher level mathematics, then certainly we will. But here in 1000 level elementary statistics, probably not. But I want to use it as an example that discrete does not always mean finite. Here we can get arbitrary positive, actually non-negative integer values. K value can be 0, 1, 2, 3, 4, 5, 6, it goes on forever. Still, they're all discrete. All those integers are apart a certain distances. So they're all discrete random variables. Mostly in this class, we are going to consider finite random variables. A random variable takes only, say, 5,000 possible values, or 764 possible values, kind of like those. But sometimes we can consider discrete random variables that may take infinitely many possible values like that. If you're interested in the precise definition of a random variable, here it is. It's actually a real valued function defined on the sample space. But just consider it as a scheme, a gambling model with payoffs.